All right, good morning, everyone. Hope you had a great weekend. We are 1 week away from spring break, so we will finish up improper integrals today, 6.6. Again, this stuff is not going to be on the exam, stuff from today. And then your exam will take place this Wednesday. So same routine as the first exam, come in prepared with your camera set up, all that. And we'll just run through the same thing. Are there any questions about that? Okay. I'm going to save some time at the end of class for any questions over, the review stuff I sent you. If there's anything you want me to go over, there will be some time at the end. I'm thinking this will take us under an hour. I'm hoping to do what we need to do today. And if there aren't any questions, then I don't know what I'm going to do. I don't know, make up problems, let you go, we'll see. So, okay, that's it. Let's get down to business. So last time, what we were talking about were the type 1 improper integrals where you would have your limits of integration would include infinity. You either had infinity at the top or negative infinity at the bottom, or you had a combination of both. And so hopefully in the homework, you're able to kind of figure out how to do that. Now we're going to talk about the type 2 infinite integrands. So these are basically integrals where you have a discontinuity somewhere within the interval that you're trying to find the area under. When I say discontinuity, I mean we have like a vertical asymptote occurring somewhere within the interval that we're trying to integrate over. So let's say we had a function that looked like this. We were trying to integrate from A to B, okay? And when we look at the actual graph of the function, what if we had this happening where this is, why isn't this working? Whoa, what's going on? Hold on, my program's not letting me draw on the screen. Let me close it and reopen it. Sometimes that happens. Okay, still not letting me. What the heck? Interesting. Okay, well, I'll have to adapt here. Man, this is all messed up. Okay, sorry, technology. Do one more thing. I'm gonna have to restart it here. Where is it? Epic Pen. Let's end it. It was just working on my previous class, so that's kind of weird. Okay, there it is. All right. Okay, so what if this was A here, and this was B, and we're trying to find this integral A to B of f of x dx, but at A, you see at A, we have a vertical asymptote. So the function keeps going up, it's going up and up and up. And so you cannot plug A into the function because it's undefined at A, which means you have a discontinuity at A. Well, the question is, can we still figure out what the area is under this, even though we have that vertical asymptote occurring? Well, it should make sense to you that, we might be able to, for the same reason that when we had a function, let's say we started at A and we went to the right, and we had it, diving down towards the x-axis like a vertical or a horizontal asymptote, we were able to find that sometimes it converged, sometimes it diverged. So if we have this vertical asymptote instead of the horizontal, it makes sense that we should be able to at least try it, right? That's the basic idea. Then we have another scenario where it's kind of the opposite. At A, there's not a problem, but at B, we have a problem. So the question again is, can we try and find the area here? And then we have kind of a combination of both, where somewhere within the interval, all right, here's A, here's B, but somewhere inside the interval, you have your vertical asymptote occurring. Can we then find the area of this, all right? All of these above cases are considered to be type 2 infinite integrand integrals, all right? And we're either going to have our function going to infinity or negative infinity at the ends of the interval or somewhere within the interval. That's what's going to be happening. So let's take a look at the very first type where we would have, let's say, a problem at the right endpoint. Okay, so let's say we were having a problem where at A we were fine, but at B our function is undefined. What we would do to do that integral is this, and this should look very familiar to you. B is where we have the problem, right? So we're going to replace the B with T, and we're going to do a limit, and we're going to let T approach B with the little negative sign. That little negative sign means from the left. So we're going to be taking this limit as T approaches B from the left-hand side. All right, that's how we're going to do it. So this is kind of like we were previous part of this section. We were replacing the infinity with T and then letting T go to infinity. Here we're replacing the point that has the discontinuity with T and then letting T approach that discontinuity from whichever side. The reason why I'm coming from the left is because our interval goes from A to B and our discontinuity is at the right endpoint. So I have to come in from the left. Make sense? Okay, and then if we have it the other way, right, where our discontinuity is on the left endpoint and not on the right endpoint, then again, we will replace, this time the left endpoint, we'll replace that A with T, then take the limit as T approaches A, but this time from the right, because again, it's at the left endpoint, so we can only come in from the right. How do you think we're going to handle it when the discontinuity is somewhere in the middle?
We break it in half.
Yeah, we'll just break it up. So if you have a discontinuity in the middle like this, where you have A is no problem, B is no problem, but there's some point C in here where you have a problem, you're going to have to break it into two integrals. You're going to go first from A to C, plus then you're going to do the integral from C to B. And since the problem is at C, each one of these is going to turn into a limit. All right. So I have this formally in the notes right here. Here's what we do. We break it into two, and then each one of those will become limits. Let's do some examples. So the first example is this one. And just for fun, let's take a look at the function 1 over x squared. We're only looking between 0 and 1. So 1 over x squared, but we're only looking when 0 is less than x is less than 1. Okay, there's the graph. Let me shrink this down. That kind of gives you some idea of what we're trying to do. We're trying to find the area. Here's 1, right? We're trying to find this area in here, but we've got this discontinuity on the left-hand side, right? So let's go after it. So here's the way I like to do these, okay? This is just my personal preference on these. What I do first is I look at the integrand, okay? I look at this integrand and I ask myself, where are the discontinuities? Where are the discontinuities? Well, to me, I look at that and it's pretty obvious that I can't plug 0 in there, right? I can't plug 0. So for us, x equals 0 is a discontinuity. The next thing I do is I look at the interval that I'm trying to integrate over, and I draw that interval on a number line. So here's my number line. Here's 0. Here's 1. I'm trying to find the area between 0 and 1, and I realize that I have a problem, right? Right here corresponds to my discontinuity. So I have a problem at the left endpoint, right? So if I try and do this integral, what I'm going to have to do is I'm going to have to turn it into a limit. And I'm going to have to let t approach 0. And then I have to come in from the right-hand side because my interval is between 0 and 1. So I have to come in from this side, which means I'm going to put a little plus on the 0. And then what am I taking the limit of? Well, the original integral with the problem point, which was 0, I'm going to replace that with t and then leave this as 1. And then I just have 1 over x squared dx. Questions?
What if taking the integral kills our hole in the hole?
What do you, what?
Like,
what-
would it be feasible for it to be in this form? The 0 would cause a problem, but once we took our integral, there would no longer be a mathematical problem with having a 0 there.
Yeah, that's right. Sometimes when you do this, you're going to get convergence,
Okay, is that
which means
that's
we're going to get a number. Yeah.
okay? Gotcha.
We'll have to see. Let's take a look. Let's see what happens here. We need the antiderivative first, right? So we're going to first find the antiderivative. And the antiderivative of 1 over x squared should be negative 1 over x. I'm not going through that work. Just remember that's x to the negative 2. And then just do your power rule on that, right, for antiderivatives. And you should get 1 over negative 1 x to the negative 1 when you use your power rule. So that's our antiderivative. We're evaluating this. Let's see, 1 on top, t on the bottom. This becomes the limit as t approaches 0 from the right. And now I have to first plug in the 1 and subtract what I get when I plug in t. So if I plug in 1, I get negative 1 over 1. If I plug in t, I get negative 1 over t. Now the first part of this is just a number, right? This is negative 1. Okay, negative 1 minus. Now what happens here? If we let t go to 0, right, through positive numbers, right, from the right, sorry, I shouldn't say through positive numbers, from the right of 0, then I have negative 1 over a number that's getting really small and positive, right? That should become what? I see Eduardo saying this. It gets huge, right? You have a fixed number on top.
Doesn't it become
It's actually
negative
fixed and it's
infinity?
negative, right? Say
Yeah.
again?
Doesn't it become negative infinity?
Well, yes, because the bottom is headed towards 0, right? And it's always positive because we're coming in from the right. So you have a negative divided by a positive. And anytime you have a fixed number over something that gets really small, it gets really big. So this should be negative infinity. So that becomes negative infinity in here. And it doesn't matter that it's negative infinity. All that matters is that it becomes infinite. It's not headed to a number, right? It's not headed to a specific number, which means that this integral diverges. Which means that that area is becoming infinite, right? It's an infinite area. And it's kind of interesting because if I ended class last time with this rule, let me see if it's here. I know I did. Hold on, where is it? You know what? It's in the notes. I know I wrote it down somewhere. Here we go. This formula that the integral from 1 to infinity of 1 over x to the p is divergent if p is less than or equal to 1 and convergent if p is greater than 1, right? So that's what I talked about last class. Here, so what I'm trying to say is this. On this integral, right? This integral, this is divergent, this diverges. However, if you were to have done this integral from 1 to infinity of 1 over x squared dx, this converges, which is kind of weird. We're saying that if you were to now take this 1 over x squared and look at it from x greater than 1, greater than 1, greater than 1, what the hell is going on here? Oh, x dot, that's what's wrong. So what we just concluded is this. If you were to look here at this area, that's divergent because it's headed towards infinity. It's an infinite area. But if you look at the area over here, right, that is convergent, right? It's headed, this is headed towards a number. So you've got like finite area to the right of 1 forever, but you've got infinite area from between 0 and 1. Make sense? So what do you think we would get? How do you think you would go about this problem? If you had integral 0 to infinity of 1 over x squared dx. How do you think you could handle this?
Gut reaction, I'd want to break it in half.
And break it up? You could break it, right? You could say, okay, this is going to go from, let's say, 0 to 1, right, of 1 over x squared dx. And then you could say plus the integral from 1 to infinity of 1 over x squared dx. And this should be what? This is a number, whatever it is, plus, but this
infinity.
is infinity. So the whole thing would diverge. It should make sense. The total area of both of them together is going to be infinite because just from 0 to 1 is infinite.
Infinity plus some number is infinity.
Yeah, it's just the idea that it's growing without bound, right? It's growing without any bound at all.
How would you know what number to pick?
You can pick any number you want. And when you think about within the actual computation we did here, imagine that this was any number, like let's just say it's to the right of 0, let's just call it b, right? Just some number b. Then this would be b, this would be b, and when we plugged in here, we would get 1 over b, wouldn't we? And 1 over b would be just some number, or sorry, negative 1 over b would be just some number, yes? As long as b isn't 0, and I said b needs to be to the right of 0. So if you pick any number, then you're going to get, this is not going to be a problem. You're not going to get infinity here. You're not going to have a problem. This will just be some numerical value, some number here. And then you're going to be subtracting. Now you can't get away from what happens at 0 though, right? So you'll still have the infinity. So it would not matter which number I went to, but 1 is just convenient. Okay, let's look at our next example. All right, so again, I'm going to start off the way I like to start off. I'm going to look at the integrand, and I'm going to ask myself, where do I have discontinuity? Well, I know that when it comes to the square root of 2 minus x, that's the denominator, right? That can't be 0. But along with that, I know that 2 minus x has to be a positive number, right? Let's say greater than or equal to 0. So by itself, 2 minus x, that can't be negative, or else I'll take a square root, right? A square root of a negative. So I need to make sure that what's underneath the radical is positive. But I also need to make sure that the radical is not 0, because if this is 0, then I have division by 0. This happens, I need to make sure I'm looking at when x is 2, I have something important happening, right? I have a discontinuity. And all this is saying here is that when you plug in numbers, x must be less than or equal to, but I'm already telling you that I have a problem at 2. This is more of like the domain without the equal, because we can't have 2 in there, or else we have division by 0. So I have a problem at 2. That's all you really need to take away from that. You have a problem at 2. So now I put my interval, I'm going from 0 to 2, right? And I have an issue, right? I have an issue at 2, right? This is where I have a problem. And so I'm going to need to approach 2 from the left. So this is going to turn into a limit. Limit t approaches 2 from the left of 2 of the integral. Now I'm replacing the 2 with t. I'm leaving the 0 as 0. And then 1 over the square root of 2 minus x dx. Okay, I'm gonna go refill my drink. Why don't you take a moment, find the antiderivative of this. This is not trig sub. Don't go doing trig sub on this. This is the basic u sub. Just do a basic u sub on this. I would do that on the side. Okay, I would be trying to do this integral, this indefinite integral without the limits of integration, and then do your u sub. And I'll be right back. Okay. Who has the antiderivative for us here?
I think, is it negative square root of 2 minus x?
Negative square root 2 minus x. Let's see.
There's a negative.
Say again. Someone say something. Is that right?
I don't think there's a negative.
No, there's a negative. It's missing a 2.
It's missing a 2. Needs to be negative 2 square root of 2 minus x. So let's just do it real quick.
Where to get that 2?
Yeah, so let's just do it. The u sub is 2 minus x. The derivative of that is negative 1 dx, right?
Yeah.
We have just dx, so I'll multiply both sides by negative 1. And then when I rewrite this integral in terms of u, it's 1 over the square root of u times negative du. So I'll put the negative on the outside, du here. That's the same as negative integral. This is u to the negative 1/2 du, right? And then that's going to become negative 1 times, now the antiderivative of this is 1 over, you have to add 1 to this, so you get 1/2, and then u to the positive 1/2 plus c. So that's where the 2 comes from, 1 over a half.
I don't know how I keep on forgetting that.
Yeah. Does that make sense, everyone? So that's where you get your negative 2, and then just square root of u is just square root 2 minus x. We want to evaluate that from, let's see, 0 to t. Are there any questions? All right. Okay, so this is going to be equal to limit t goes to 2 from the right. Okay, I'm going to plug in my 2 values here. So first I plug in t, so negative 2 square root of 2 minus t. And then I plug in 0, so negative 2 square root of 2 minus 0. The second one is actually not that bad. It just turns into a plus 2 root 2. Because, well, 2 minus 0 is 2, and square root 2 is 2, and negative negative is positive. So we just get this. Over here, right, I'm going to figure out what happens when that t goes to 2 from the left. Now, it actually doesn't matter that we're coming in from the left, or it does. What do you think? Does it matter we're coming in from the left?
It does, because if it came from the other way, it would be a negative number.
That's right. If we were coming in from the right, This would be 2 minus 2, but the number would be a little bit bigger than 2. And then you'd have a negative under, it would be a negative number under the root. So that's not okay. But if we're coming in from the left of 2, it's like 1.999. If we plug that in there, then we're going to have 2 minus 1.999. It's a very, very small positive number, which we can take the square root of. You'll see what I'm saying? If we came in from the other side of 2, it would not work. So, but at the end of the day, it just really looks like 2 minus 2, which is 0, right? Which kills all this off. That's headed to 0. So your answer here is just 2 root 2. So it converges, right? Finite area. I think we should take a look at the graph. I have it in the notes. So this is the graph of the function. We went from 0 to 2. What we're saying is that this area here is finite. It's actually converging to 2 root 2. That's what that area is converging to. Okay. Well, what about this one? All right, so I'm looking at this. And now what I need to do is I need to take a look at the integrand and I need to talk about what x can't be. So that integrand is 1 over, it'd probably be best if I factor out an x. And then I realized that from this, that x can't be 0, right? I have a problem and x can't be 4, right? 0 and 4 are the 2 issues I have. Now I'm integrating from 1 to 4, right? I'm only going between 1 and 4, which means I only have an issue at 4, right? The 1 isn't even an interval I'm talking about. So I'm not worried about that one, right? Not worried about the 0 at all. But I am going to need to approach 4 from the left, right? I'm going to have to approach that 4 from the left. So this integral will now turn into the limit as t approaches 4 from the left of the integral from 1 to t, replacing the problem, right? We have the problem at 4. So replacing that, and then I'm going to go ahead and leave this function factored. Why do you think I'm going to leave it factored?
Partial fraction decomposition.
Yeah, I'm going to have to do partial fractions to integrate this over here on the side. I'm going to take 1 over x times x minus 4. And I know that those are 2 distinct linear factors. This is going to be on your test, right? In 2 days. So I need to be able to break that up into 2 pieces like that. A over the linear and B over the linear. Clear the fractions. And then either use the short method or the long method to get A and B, right?
Use short method on this one.
Yeah, short's going to work out pretty quick because for the short method, I can just let's start off, let's get A. So I'm going to let x be 0. That will kill off the B term. If I do that, I get 1 equals, let's see, if x is 0, I should just get negative 4a, which means that a is negative 1/4. And then to get b, I'm going to let x be 4. That'll kill off the other factor, or the other term, I should say. And this will be equal to, let's see, if we plug in 4, that's gone, and then I get 4b, which means that b is positive 1/4. Is that all right, everyone, what I'm doing there? Yeah. So now here's where we are. We have limit. T goes to 4 from the left. Integral from 1 to t. And now I have my broken up thing here. The a is negative 1/4, so I'll put negative 1/4 over x plus b, which is positive 1/4, over x minus 4. And that's something I feel more comfortable integrating, right? Because I just have constant over linear, constant over linear. Anytime we have constant over linear, we're just going to have natural logs, right? So antiderivative time. Okay, the antiderivative of this should be a negative 1/4 natural log of the absolute value of x plus positive 1/4 natural log of the absolute value of x minus 4. Evaluating that from 1 to t. Questions there? No, we're all right with this?
Professor, just to clarify, can we use the matrix? Actually, never mind.
Yeah, you could. Well, I don't even know if you would need a matrix, but you could
No,
do the
you don't.
long way where you expand it all out and you get a system of equations. Yes, you just do that.
Cool. No, sorry about that.
No, it'll just take a little, I think that would take a little longer personally, but you can do it. Not much longer, not for that problem. It wouldn't be too bad. Okay, so let's see here. I need to now evaluate this, right? Before I take the limit, I need to evaluate at the two endpoints. So I'm going to plug something in, subtract, and plug something else in. So I start with t going in for x. So natural log absolute value of t plus 1/4 natural log of absolute value of t minus 4. And then I plug in 1. So negative 1/4 natural log of 1 plus 1/4 natural log absolute value of 1 minus 4. You can see now why that absolute value is so important. Because if you didn't have the absolute value here, this would be the natural log of -3, which is undefined. I'm going to handle this first. This is just equal to 1/4 natural log of 3, whatever that is, because natural log of 1 is 0, right? We should know that from college algebra. Natural log of 1 is 0, so this is gone. And then here, like I just said, 1 take away 4 is -3, but take the absolute value. That means natural log of 3 with the 1/4 in front. So that's here minus. So that's not a problem. That's just a number. And then over here, let's see what happens as t goes to 4 from the left. Okay, so when t goes to 4, this becomes minus 1/4 natural log of just 4. That's not a problem, right? Natural log of 4 is whatever the natural log of 4 is. Then plus 1/4 natural log of, here's where we have a problem. Because if t goes to 4, 4 minus 4 heads to 0, right? So this thing is headed to 0. And what does the natural log function do as you head to 0? So you got to remember what it looks like, right? Natural log looks like this.
It's heading for -infinity.
Yeah, it heads down to -infinity. So this heads to -infinity. You have to remember, I'm not saying, this right here, I'm letting t approach 4. So I'm not saying that it is 0, right? I'm not saying that this becomes 0. I'm just saying it's getting closer to 0. And it's always positive because I have an absolute value, which is why we're approaching from the right side. And I know that that's headed to 0, right? This is in the limit. It's headed to 0. And that whole expression then in the limit would be headed to -infinity. This is just a number. So I have a number plus -infinity and then minus a number over here. So that's infinite, right? -infinity, and that's divergent. Good problem, right?
I'm a little confused. So we
Okay.
insert our values and then we evaluate after that evaluation.
Well, Are you talking about t? You're inserting the values for t, or are you talking about inserting values for 1?
Yes, sir. For 1 is just value, but
Yeah, that is a fixed number 1. When we insert the value 4, we're not actually putting 4 in there. We're saying what happens as t gets closer to 4, right? If you let this number get closer and closer to 4, then those two numbers together, they approach 0, right? They approach 0. And
Yeah.
then you're saying, well, what does the natural log function do as you approach 0? And that's this picture. As we move, here's 0 on the x-axis. The natural log function, as you approach 0, it starts to dive down and get really, really big but negative. So it heads to negative infinity.
perfect. So we're just basically using a test point, and then we'll like assess through there.
A test point like what? What do you mean?
Like for example, I guess for me to wrap around it is like I use visually like what a test point is. So for example, at 0, we're gonna go to negative infinity. Like that's where our test point is 0 or whatever. And then I don't
Well,
know
you
if I'm saying
can't,
it
the
correct.
problem is you can't like go on your calculator and plug 0 into your calculator. I mean, sorry, natural log of 0, because it'll give you an error because it's undefined. It won't tell you negative infinity. You have to imagine that this number right here is really close to 4, right? So it's like 3.9999, okay? If you plug that in here, 3.9999 minus 4 is going to be a very small number, like 0.00001, sorry, negative. But then it's got an absolute value around it. You take natural log. If you were to plug natural log of negative 0.00001 into your calculator, you would get a very, very big negative number. But I am not a fan of thinking of this as test points as far as like trying a number. I think it's better for you to understand like what's going on. This is approaching 0. What is the natural log function doing as you approach 0? Well, you come in and you look at it graphically, mentally, right? This should be a mental graph in your mind of what natural log looks like as you approach 0. You should be going, that's diving down to negative infinity. Therefore, it diverges.
Gotcha. With that explanation, that clears up everything. Awesome.
Okay, good. Anything else on this one? We're good. Here's the picture, just so you see it. That's what it looks like. Let me see here. Okay, yeah. Now there's something very subtle here, okay? Before I do this example, let me put it here first, but there's something very subtle that you have to be extremely careful with now, and that is this. If I were to ask you, what's the antiderivative between -1, let me do this one, between 0 and 3 of 1 over x minus 2 dx. Just think about this for a second. If you get all gung-ho on me here and be like, oh, well, I know the antiderivative of that is just natural log of x minus 2, you'd be correct. That is the antiderivative. And then you say, I'm just going to evaluate from 0 to 3. And so you plug in 3. If you plug in 3, you get natural log of the absolute value of 3 minus 2. And if you plug in 0, you get natural log of the absolute value of 0 take away 2. So this is natural log of 1 minus this is natural log. Let's see, that's -2, but then absolute value is natural log of 2. Natural log of 1 is 0. So you might tell me that the answer is negative natural log of 2. And you'd be wrong, right? Why are you wrong?
Because there's a hole.
Yeah, because you have a discontinuity at 2, right? And 2 is between 0 and 3. You missed it. And so you did all this and it's all wrong, which means now we have to pay attention to our integrands and make sure there aren't any discontinuities in the integrands. Every problem we've done up until today, we have carefully avoided any problems with the integrand. Okay. Now, most of the problems we've done in the past have been improper integrals where we had no limits of we have had, I can't think today, I'm sorry. Indefinite integrals where we don't have limits of integration, right? That's what we've been dealing with until a few days ago. And that's when we finally put the numbers on the top and bottom. Now that we have the numbers on top and bottom, now we have to pay very careful attention to make sure there's no discontinuities within the intervals or within the interval. Oh, okay, that all makes sense? So careful, this is all wrong. Let's get to this one. This is a good illustration right here. So I'm looking at this and I'm like, okay, first things first, let's take a look at the integrand. Where do we have a problem?
At 4,
At 4. Is 4 in our interval?
yes.
Yes, right? We actually have a problem. Now, this is the first time that the problem is inside, right? The problem is inside, not at one of the edges. So here's what I'm going to have to do. I'm going to have to take this integral and break it up. Go from 3 to 4 first. And then add to that and now go from 4 to 5.
Professor, wouldn't you want to add that that plus, no, that negative on the top? So 4, -1, or negative?
Yeah, you mean
approaching.
which side I'm approaching 4 from?
Yes, sir.
I'm going to do that in the next step when I actually put the limit in. Because right now, all I'm doing is saying, okay, instead of going from 3 to 5, I'm going to go from 3 to 4, then 4 to 5. And now each of these will turn into limits. And that's where I will talk about the actual approaching. So for this first one, I'm going to take the limit. Now remember, our problems are at 4, right? This one represents that side. This one represents that side. So when I do the yellow one, I'm going to let t approach 4 from which side? Left or right?
Left.
Left. And I'm going to go integral 3 to t and then x over cube root of x minus 4 dx plus now the other one. So limit. Now I'm going to approach 4 from the right because I'm talking about the blue region. I'm going from 4 to 5. So when I approach 4, I need to come in from the right side of 4. And this will go, oh, sorry, that should not be x. I apologize, down here. That should not be x. I can use t or I can use any other variable here. I'm going to use r. I'm just choosing, that's my choice here. Then r to 5, and then x over cube root of x minus 4 dx. Okay. Why don't y'all take a minute to see if you can do this antiderivative, because we need this antiderivative, right? Take a moment to see if you can handle this. I'm going to step away for a minute. I'm going to start working that integral out. See if you get what I'm doing here. What do y'all think of that integration? Basic U sub. Right, basic U sub, you can rewrite it. The big thing is to realize you can replace the X with the U plus 4 by solving for X.
That's
And
what
once
tripped
you
me
do
up.
that, yeah, you split it up. So, I mean, that goes back to like the very first technique we learned, right? Substitution. So we've learned so much since then that you start to see these things and you might try and overcomplicate them because you got all these different things and you're trying maybe like integration by
I was
part,
trying to
this,
integrate by
that.
parts.
Yeah, so you can get yourself really kind of hung up with other methods. Not to say it couldn't come up, integration by parts or something else. I mean, the previous problem, we did partial fractions. So, you know, it's all on the table at this point. But go ahead and, you know, turn it into this, and then you split it up into 2 fractions, rewrite the cube root of u as u to the 1/3, just exponent rules there, and then your power rule for the antiderivative. Questions? Okay, hold on. So I want to share something with you all, just so you all know. This week has been real hectic for me. So I'm really kind of far behind. Actually, the last 2 weeks have been real hectic for me. And I realize we all have life, you know, we have a lot of things going on. But within the last like 10 days, I've been to 2 funerals, and I had to put my dog down on Thursday, Friday, I don't even remember. But it's been really hard because it was my dog and had him for 9 years, and it was really tough. And he has another partner dog here in the house that's been with him for 9 years. So like now I'm having to keep an eye on him and make sure he's okay. So if you heard him barking a minute ago, he's looking for his friend, right? He can't figure out where he is. So anyways, I'm kind of distracted here, just so y'all know. You know, relatively speaking, with everything else going on in the world, my problems are minor, but I just want you to know my mind is kind of wandering. If any of you have, you know, are dog lovers, you understand that, you know, dogs are better than most humans, right? I mean, it's just the way it is. So anyways, if I make a mistake here, you see something obvious. I made a mistake earlier today in my other class. I'm just kind of what's the word? Just kind of going through the motions at this point. So anyway, let's continue. This is going to be a lot to write. So I don't know if I have enough room to do this. So let me see if I can't grab this and just move it down here. Okay. So let's do this first integral. I'm going to do this first one in red, and then I'll do this one over here. I'll do it in green. Okay, so for the red one, I'm going to have a limit as t goes to 4 from the left. Okay, I need the antiderivative, which is 3/5 x minus 4 to the 5/3 plus 6 x minus 4 to the 2/3, evaluating that from 3 to t. Okay, I've got to do that. And then on the other one, I've got to do plus, and now I need to limit. R is going to go to 4 from the right. And then it's that same antiderivative, 3/5 x plus or x minus 4 to the 5/3 plus 6 x minus 4 to the 2/3, evaluating that from R to 5. All right, here we go. Let's now evaluate each of these. This is where I think I'm going to start to run out of space. Okay, let's plug in t first. So when I plug in t, I get 3/5. I've got t minus 4 raised to the 5/3 plus 6. And then I've got t minus 4 to the 2/3. Okay, that's what I get when I plug in t. And then minus, now I need to plug in 3. So 3/5, 3 minus 1 to the 5/3 plus 6 times 3 minus 4 to the 2/3. That is done. Okay. Same thing with the green one now, right? Same thing with the green one. So plus limit R goes to 4 from the right. Yeah, I'm pretty sure I'm going to be tight on space here. I'll do my best. 3/5. 5 minus 4 to the 5/3 plus 6 times 5 minus 4 to the 2/3. Okay, and then minus, now we plug in the R, so 3/5. R minus 4 to the 5/3 plus 6 times R minus 4 to the 2/3. Did I get it all in here? I think I did. All right, I think I'm ready. I'm gonna go ahead and let's just see what happens when T goes to 4 from the left. Well, if I plug 4 into here, right, into here, 4 minus 4 is 0. Yes? So that's headed to 0. 0 to any power other than 0 is going to be 0. So I think this whole thing is gone, isn't it? Everything here is going to go to nothing. That's good. Minus, okay, over here, let's pay attention to this. 3 minus 4, that's -1. And what's -1 raised to the 5/3? What's -1 raised to the 5/3? Well, that's really -1 to the 5th power, and then take the cube root. So -1 to the 5th is -1. And then the cube root of -1 is also -1. So I get -1 there, right? So 3/5 times -1 plus 6. And then same principle here. We have -1 to the 2/3. -1 to the 2/3 is the same as -1 squared, but then take the cube root. And that should be 1, right? That should just be 1. That's that. Okay, so all of this to get, well, I'll do it on the next line. Hold on, let's keep going. Plus, okay, if R goes to 4, all of this again goes to 0 because you're going to have 4 minus 4 is 0, 4 minus 4 is 0. So all that's going to vanish away to nothing. And then here, thank goodness, this is just 5 minus 4, that's 1. And 1 to any power is 1. So these are just going to turn into 1. So I should have here, how do I want to do this? Plus 3/5 times 1 plus 6 times 1 minus nothing. Which is, okay, this right here is going to be -3/5, but then I'm subtracting it, so that's 3/5. And then this is going to be 6, but I'm subtracting it, so that's -6. And then over here, I have 3/5, and then I have plus 6. And the 6's cancel, and 3/5 plus 3/5 is 6/5, which means we have convergence. The area is finite. Questions? That's a lot going on there, huh?
How does it take account of that missing slice, like that missing piece? Is it just so statistically insignificant, or?
No, it's that if you look, I guess the best way that I can explain this is we're trying, let me go look at the picture. This is the graph of the function, right? Wait, is this it? Hold on a second. That doesn't seem like that's right. Did we get all our signs right? We didn't mess up signs, did we? That picture makes me think it should be something different, but let me see, this was 0, T was on top, R was on the bottom, 3 minus, yeah, this one was 1. Okay. Let me answer your question first. Your question is, what about the slice? So it was between,
You can graph it real quick.
yeah, I will, hold on. But it was between, the original problems was between 3 and 5, right? Between 3 and 5. So what we're basically doing here is this. We're saying we want to go and find the area between 3 and T, okay? And then we want to find the area between R and 5. Okay, so imagine there's some function up here, function there, and we know that we have some asymptote happening. This is where 4 is, right? That's 4 right there. We know that we have an asymptote. What we're doing is we're finding the area between 3 and T, and then R and 5. And then what we're doing is we're letting T approach 4. So this area, right, that area, as we move to the right, that area gets closer and closer to 4 without actually getting there. But this area is just a finite number. And then on the other side, we let the R start head towards 4 from the right. And this area here is also headed towards a number. Neither one of them are becoming infinite. And so we're not excluding the 4. We can't plug 4 in. We're just kind of like letting it shrink. These two middle pieces, these two vertical pieces, blue vertical pieces, are getting closer and closer to 4, smashing it in. And the closer we get to 4, the closer the area gets to 6/5. It's a limit. It's approaching 6/5. It's getting closer and closer and closer and closer and closer and closer and closer. The more you squeeze it, the closer you get to 6/5. You'll never exceed 6/5.
We just measured it in an infinite amount. So then we can move on.
I think yes is the answer to your question. Let me graph it. I'm a little concerned about this now. Raised to the 1/3. Where did we integrate from? From where to where?
3 to 5.
Okay, 3 less than X less than 5. Okay, now I'm okay. Let me put the asymptote in there. X equals 4 and dotted. Okay, there we go. So I'm okay with this answer now. And the reason I'm okay is because these aren't symmetric. I thought from my picture, it looks symmetric. From my picture, it looks like these are equal, right? Kind of like they should offset each other, but there's a slight difference in these. And you can really see it when you look at this graph. If I include the whole graph, let me do it this way. I'll duplicate that. Done. And then here, let me cut this one off. Make this one blue. Okay, so what you can see here is that we're going between 3 and 5. So we're going between 3. Here's 3. We're trying to find this area here. Okay, that area in there, all the way down in there. And then we want to add to that the area between 4 and 5, which is this area. And I hope that that picture shows you these are not like the same areas, one of them positive, one of them negative. You can see that they offset each other, right? I mean, they don't offset each other. We have more area here than here, which is why we're getting a positive 6/5 as an answer. Is that okay?
Perfect.
All right. Let's continue. Let's see what else we have here. Yeah, this is our last one. Why don't I let you enjoy this one? See if you can figure it out. I think the integration is probably the big kind of trouble spot. You also need to make sure you're paying attention here. There's, you know, you've got to be looking at domain, right? See what happens. I'll give you, let's go 10 minutes, okay? And that'll leave us 30 minutes to talk about the test. 10, 15 minutes for the rest for this problem. Can y'all still see my screen?
Yeah.
Yes, okay. I paused my share screen, so I'm gonna write, but you won't be able to see it, but I didn't know if it turned off the screen for you, so. I just sent out a poll. I just wanted to know if anyone has finished it, just just say yes. If you haven't, just wait. When you finish it, click yes.
Finish the integration or finish the whole problem?
Let's just go with the whole problem. I'm going to go another 2 minutes and then we'll talk. I'm hoping everyone at least will have it up to the point where you've found the antiderivative and, set everything up and then have to figure out the limit. So the limit is tricky. Okay, so I had 3 people said they finished. So let's see. Y'all can let me resume sharing my screen here. So on this integral, first you have to realize that there's a problem at 0, right? There's not a problem at 1. The natural log of 1 is 0, but that's not an issue. 0 on top's okay, 0 on the bottom is not okay, right? So we only have an issue at 0. We're going from 0 to 1, so we're going to need to approach 0 from the right-hand side. I didn't put that there, but we're going to need to approach from the right. So I take the limit as t goes to 0 from the right. I replace the 0 with t to 1. Here's the integrand. Then I have to go do my antiderivative. So I split this natural log over the square root of x up into the natural log of x times 1 over root x, and then I used integration by parts. Here's my integration by parts formula setup. Notice on my integration by parts, I stopped using u and dv. I just set up the table. That's just kind of faster. So I know I'm going to take derivative of this and get 1 over x dx. I'm going to take the antiderivative of this. Be very careful here. The antiderivative of 1 over root x. I'm not showing any work for that, but it's 2 root x. And then I use the formula, ultraviolet minus the integral of voodoo. I bring the 2 out. I multiply 1 over x dx times root x. That gives me a 1 over root x. Again, I have to find the antiderivative of that, which is 2 root x. That comes together. The 2 2's become a 4. And that's my antiderivative. And I take that, put it right here. Limit, t goes to 0 from the right. Here's 1, here's t. Plug in 1, boom. Plug in t, boom. Questions there. Questions up to that point. It's all okay?
I just gotta say that I'm very happy to see that that's what it is, because as a rule, integration by parts, I feel like I did something wrong.
Yeah,
Just, I always look at them and go, that doesn't look like the right answer. It never does.
yeah, it never does.
And I'm sitting here going, yes.
You can take the derivative, right, if you want to check it, but you know, yeah, I understand what you're saying. It never looks the way you think it is. Let's see what happens here. If I try and evaluate this, this is just 2 times natural log of 1 is 0. So 2 times 0 is 0, minus 4 times the square root of 1, that's just 4. So we get 0 minus 4, it's -4 here, right? That's what I get for this first piece. Minus, now over here, we've got some issues. When t goes to 0, let's talk about this one. When t goes to 0, that just becomes 0. So we're not real worried about that. This is the piece that's trouble, okay? Because when t goes to 0, this goes to 0, and natural log of 0, well, natural log of 0 is undefined, but as t heads to 0, where does natural log go?
Negative infinity.
Negative infinity. We've just talked about that, right? So you have something that's headed towards 0 times something that's headed towards negative infinity. That is not necessarily negative infinity or 0. That's an indeterminate form, which means I have to go over here and I have to do some more calculus. This is Cal 1 stuff. So I've got to take the limit as t approaches 0 from the right of 2 square root of t times natural log of t and figure out what it is. I already know that this heads to 0 times negative infinity. That's what we just said. So the standard procedure for this is to take one of the 2 factors and drop it to the denominator. So here's what I'm going to choose. I'm going to choose to drop the root t down. So I'm going to have 2 natural log t on top. And on the bottom, I'm going to have now 1 over the square root of t. Now, the reason I'm doing this is because now if you let t go to 0, we know the top already goes to negative infinity, right? Because when you try and plug 0 into natural log, you approach from the right, it dives down to negative infinity. But by doing this and rewriting this as this square root of t on top as a 1 over root t on the bottom, now if I let t go to 0, this becomes 1 over 0, and that becomes infinite as well. Fixed over something getting small gets big. Now I have infinity over infinity, so I can apply L'Hopital's rule. So now saying with L'Hopital's rule, I can take the derivative of the top and bottom separately. The derivative of the top is 2 times 1 over t, because the derivative of natural log of t is 1 over t. 2 just comes for the ride. And then the bottom, remember, be careful here. This right here is actually t to the negative 1/2. That's what's on the bottom, right? And when I take the derivative of that, I get negative 1/2 t to the negative 3/2. So that's what's on the bottom. Negative 1/2 t to the negative 3/2. And that may look bad, but it's actually not. Let's just keep cleaning this up algebraically. The top is 2 over t. That's one way I could write that. And then the bottom, watch the way I write this. Negative 1 over 2t to the 3/2. So I'm just kind of taking that t to the negative 3/2 and dropping it down as a t to the positive 3/2. The reason I did this is because now I have a fraction over a fraction. And when you have fraction over fraction, you can multiply by the reciprocal. So instead of dividing by that fraction, I'm going to multiply by the reciprocal. So I put 2t to the 3/2 on top, and I put negative 1 on the bottom, and I get rid of this down here. You having fun yet? Limit t goes to 0 from the right. Okay, let's see here. I'm going to clean this up. This is 4 on top over, let's see, that's a negative 1 on the bottom. I'm putting the t's together. T to the 3/2 over t, right? You subtract powers, 3/2 minus 1. That's t to the 1/2, isn't it? Which is the same as the square root of t. So I'm just going to write the square root of t on top. That should be what we have now after we clean this up algebraically. And if I let t go to 0, 4 times 0 is 0 over -1. This is 0. So that limit approaches 0. So this heads to 0 minus 0. Which means what happens here? What the hell's happening?
It's all approaching -4.
It's all approaching -4, which means we have convergence. Which means that if I look at this graph of this function between 0 and 1, it's probably below the x-axis because I'm getting a negative area. Questions? Let's look at the graph. There it is. Yep. Between 0 and 1, you can see the graph's below the x-axis. And so I got -4, it's convergent. It's a finite area. We're done. Page 361 through 31 odds. You've already done some of those, right? Last class, I told you,
Like most of them, actually.
yeah, I think I told you go through 1 through 21. So there's like a couple of more problems now. Those will have the type 2 issues going on where you have some discontinuity in them. And that's it. That's it up to exam 2, which will be next class, and then our spring break, and then we start chapter 7, which is
And this-
applications of integration. So we actually start to do something with this now. Was there a question? I thought I heard someone say something.
Yes. These next homework problems are due tomorrow.
No, well, is that what it says?
Yeah, it says second
Yeah,
part
you know
due.
what? Let's just make them do when we come back from spring break. That's
All right.
part of why I mentioned to you earlier about all the crap I've been having to go through. I'm so behind on homework right now, like just like checking to see, not just you, I mean, my other classes. I'm gonna get caught up over spring break, so don't worry about that homework. Worry about the test. Worry about the material on the test, and then just when we come back from spring break, you can submit your work for the second part of 6.6. All right,
It's everything before today is on this test, right?
that's right. Yeah,
Cool.
so you will not see a definite integral with a discontinuity in it with the limits of integration containing that discontinuity. That won't be there. I think on the review, one of the reviews, I told you to skip a problem or something. Did I tell you all that? It was, I think it's because it's that type
Yeah.
of problem. And so we technically didn't know what to do with that. Now you could do it, but it won't be on the test. Any questions about the test? Any of the, did I give you a 1 review, 2 reviews? How many reviews did I give you?
I think he gave us,
Just 1,
Luis is saying 2.
2? It was in an email, right? I sent you
I
an
think you
email.
showed 2.
Yeah, I probably showed a few. I probably shown a few of them on camera, which you'll just have to go back and look at if you want. So are there any questions? Do you want me to go over anything in particular? Do you want me to just like come up with like some random problem, or, do y'all feel?
Do you know how long the test is gonna be?
I haven't made the test, so I'll probably make it. Well, your class, I don't have time in the morning, so probably make it tomorrow, if not later today.
So I have a question, just kind of not necessarily related to the test, but kind of.
Mhm.
So with the limits, the more I'm doing of them, the more I'm realizing that, man, I forgot a lot of my limit stuff.
Yeah.
Where would you recommend going to refresh myself on that? Just like your old class videos?
Did I put something in the chat last time, a link to my playlist?
I think you did, but
Hey, does anyone have that link still? Maybe you can post it in the chat. I don't know if anyone has it, but
cool.
you could just go to, yeah, the problem is finding it because my lectures are never really set up so that
Because
it's
searchable.
searchable.
Last class, the limits that we encountered, I'm sitting there going, oh yeah, I remember all of this. And then over the homework and then the stuff we did today, we hit multiple that I was like, oh God, I don't remember this stuff.
Yeah, let me see. I know I have, let's see.
Check the chat. Check the chat real quick.
Chat.
That's
has
it.
Where is it? Where the heck is it in here? these are older videos. Yeah, here's L'Hopital, but yeah, I sent, so here's a video where I do like a screen capture. I'll share this one as well. That's also kind of over limits in L'Hopital's rule.
Coolness, because yeah, I remember a lot of the basics, but there's a lot of stuff that I was sitting there. I kept hitting stuff and going, oh God, I don't know what to do with this stuff. So
Yeah. Okay, anything else?
Hey man, I just wanted to reach out and say I'm sorry for your losses, and I hope you find healing in that, man.
Yeah, thank you. Appreciate it. Yeah, today, I sent an email earlier. I will not be in my office hours directly after class. It's totally unrelated. I have to take my daughter to a volunteer thing at the food bank, and we're supposed to be there at 1:30. So I think I'm gonna have to get out of here like pretty quick. But I will be in my afternoon office hours, but they're gonna be delayed 30 minutes. Normally I go from 4 to 5. I'm gonna go from 4:30 to 5:30. Just because the volunteer thing ends at 4, and then we have to get back home. So it's gonna, put me back. She's on spring break this week, and there's a few things we have going on. So today's volunteering. So yeah,
always fun.
yeah. She has to do it for her school. She's in private school, and they have to do 2 volunteer things every quarter. So yeah,
It's good for you.
yeah. No, I'm excited
Perfect.
for her to do that. For her to do something like that. She hasn't done it before. So okay, if y'all run into any issues, between now and Wednesday, what can you have on the test? Your formula sheets, right? Make sure that you have that stuff printed out, right? Because again, you can't use your computer, but you need to know like what you have, right? Especially that trig sub thing, like that's very useful to have. Because it gives you like what the substitutions are, and then also for the trig integrals, what you do in certain scenarios. So please make sure you have that stuff ready to roll. And otherwise, yeah, just reach out if you have any questions.
Besides the reference sheets that you gave us for us to print out, what else can we print out from the files, the formula sheets?
Yeah, anything in that folder. So there's, let me see, there's a folder that says, stuff you can have on the exams. You can print everything there, but just some of it's not useful because we haven't talked about it. So let me see here. I sent it backwards. So here's our class, right? Yes. So we go to files and formula sheets. There we go. Everything here you're allowed to have. So, I actually put limit
sweet.
summary here. Okay, well, I
Awesome.
put it here so you can use it. That's
Yeah,
fine.
that was why I was asking, because I remember from
Yeah.
that folder, the limit summary last
Yeah.
class, you said we couldn't use it because that was for
Yeah, I
the
did say
Calc
you
1.
couldn't, but I put it in here so y'all got lucky. It's fine. It's not a big deal.
All
You need
right.
you still need to know how to use it. So
Yeah.
anything. So out of these formula sheets, the only ones I think would be beneficial. Let me just tell you the ones that I don't think would help. Maclaurin series table, you have no idea what we're talking about there. Series convergence test, you have no idea what that's about. All the others, the RREF instructions, that's how to use your calculator to do a system of equations. Although I do not plan on giving you something on the test that's going to require you to do like 4 equations, 4 unknowns, where you can only do it on your calculator, or it's going to take you 45 minutes to do it by hand. Everything's going to be pretty like, tailor-made so that you can do it within time constraints, right? But you still have to be able to know what to do, like execute the process. So
It'll be challenging, but there won't be anything where it's like, hey, do algebra for 4 hours.
exactly.
So I think the big one I need to grab is that trig integral one.
Yeah, that's a useful one for sure.
I have most of the others printed out from your Cal 1 class, because a lot of them are the same.
Yeah,
But this is the big one that I don't have. Mostly that table, that table in its entirety is.
That's really useful. Remember though, again, on this table, that it doesn't tell you what these square roots turn into. Okay, And in our lecture notes, I do tell you what they turn into. So just make sure you're aware of that, because when come the test, you don't want to be like, oh crap, this doesn't have it on here, right? So it'll be an interesting test. I mean, there's not going to be a ton of problems on it. There's not, you know, I think I told you like 6 to 8 problems probably, right? I can't imagine it being more than 8 because you only have 100 minutes. So 100 minutes minus how long it takes us to get set up, right? So you're going to probably only be about 90 minutes, you know, best case scenario. So I'll keep that in mind when I make the test. And I would anticipate that you're going to run out of time. I'm probably going to make it long enough where everyone's going to run out of time, and then I'll probably wind up maybe throwing out a problem or something. Just because I want to make sure that I cover everything, but just, I mean, you know, these problems take a while, right? They just take a while. And if I gave you 4 problems, you might be happy about that. But if you miss one, like, you know, it's over.
Yeah, no.
You know, and then I give you a problem that you didn't study very well or something, you know, and it's like automatically you're at a C just to start, you know. So it's kind of tricky.
You have, is the time constraint, is that something that the school requires, or is that something that you put as we should be able to do it in this much time?
You mean, are you asking me?
The fact that we have 100 minutes for the exam, is that the school says we should be able to do it, or is that you teaching think we should be able to do it in that time?
Well, the 100 minutes is just because we have to do it within our class time, right?
Okay.
That's where the 100 minutes comes from. And then, you know, my thinking is I try and make a test that I believe you can do in 100 minutes, which my rule of thumb for that in the Cal 2 class is it should take me 20. Right?
Yeah.
So I make the test, it should take me 20 minutes. Right. And now, but I mean, that's me moving very quickly also.
Yeah.
It's not me like showing, when I do problems in class, I try and show a lot of the work, right? Like all this stuff, like when I do that limit, I might do that mentally when I'm doing it. I'm not necessarily doing all of this. So even though it takes me 20 minutes, I'm cutting across a lot of corners, right? That I know you won't be cutting across, but still 1/5 of the time it takes you, I think, is a fair thing. So that's usually the rule of thumb for Cal 1 and 2. And usually when I do the review, when I do the test and I take the test, when I have the key that I use, I actually write how much time it took me for each minute, or like for each problem. So I'll just start a little stopwatch, and then I'll do the first one, I'll write the time, the second one, and I'll see which one took me the longest. And yeah. All right. Anything else? I mean, I'm not in any rush here. I do need to I'll bail at 12:40, but if there's no more questions, you're free to go. If not, you know, we'll see you.
Thank you, sir.
All right.
Nice rest of your day.
All right. You as well. Have a good one.
Bye.
Bye. I see you talking. I hear nothing. I'll wait. Yeah, type it. That's cool.
Sir, I just wanted to say,
Oh, there it goes. Now it's working.
sir,
Yeah. Yeah.
I just
Wait.
wanted to.
Ricardo, sorry, Ricardo, you were talking and Brandon
Yeah, I
was,
saw Brandon
it
talking.
looked like I was hearing him. Go ahead.
Oh, I was just gonna say, yeah, I know what you mean about the dogs.
Yeah.
The dogs mean a lot to me.
Yeah.
When you said that, I was like, oof, like I couldn't imagine having to put my dogs down. It's pretty. I love them to death. Like,
Yeah.
I have hair on my clothes all the time. Sometimes I think I eat their fur. Like,
Yeah.
I'm like, dude, that's a hair, and I'm like, Gemini,
Yeah.
that's your hair. But I love them so much.
Yeah.
Like, I mean, I really.
Yeah.
couldn't love them.
There's been a lot of hard things, but the one thing that I'm really struggling with right now is he would lay on different things, right? So like he's got like a blanket that he'd lay on, and it's like I can just still smell him, which is, and I refuse, I don't want to wash anything yet. I haven't gotten to that point, but I know that the other dog can smell him too, so I'm like, how do I deal with that? But
Oof.
yeah, I mean, putting a dog down is not easy. Have you ever had to do it?
No, these are my first two dogs, and I've had them for, one of them is 2 years old, and I've grown so attached to them.
Yeah.
I couldn't live without them, honestly.
Yeah. I mean, it was brutal, man. It was brutal, but he had liver failure, right? So it was over the last month. It's been, well, over the last year, he's been slowly kind of going, but it's that fine line where you don't want them to suffer. And he was still having good days. He was still getting up, but he was just struggling. He didn't have energy. He just was starting to not be himself. And the last thing I wanted to do was like take him in when he wasn't himself, right? Where I'm just like taking this like shell of a dog to the vet to put him down. I wanted him to still be aware. I wanted him to not be scared. I wanted him to be comfortable with me there. And so in terms of like that aspect of it, oops, am I still recording? Yeah, I'll stop recording. There's no need for that.